of the University of Texas. That's my main job. I also moonlight at Amazon as an Amazon scholar. I'm actually the only academic that's sort of embedded in the team there that's in charge of Mechanical Turk and other things. So I'll just give one quick shout out about that and then kind of go on with sort of the academic stuff. Let's see here. Yeah, so our team is under Amazon Web Services. We manage 3 products: Mechanical Turk, Ground Truth, and Augmented A2I. So brief things to say is if you have trouble finding people at Amazon to talk to about Mechanical Turk, feel free to give a shout out to me and I can help connect you with the right people. There are also research awards that they provide cash and AWS credits that we fund every year. So that's also an option to know about. There's options for faculty interested in summer, sabbatical, or longer engagements with some links here, and also lots of opportunities for internships and full-time work. And I'll put my slides online afterwards too, so anyway, you can take a look at that.
Are you sharing your slides right now? I don't see them.
Oh, thank you. Well, what do you see? Let's see. I'll try. Sorry, Aaron.
Yeah, I believe I see them. I see something that says human in the loop services.
Yeah, okay, great, okay. So I'm gonna keep on going then, assume they're visible. Okay. The other quick thing to say, so I and a lot of the researchers I know coming maybe for a computer science background have been working in this conference called Human Computation and Crowdsourcing. The first one was 2009, where we had 4 years actually of workshops, and the conference has now been going on for quite a while. There's one coming up in a couple of months. So this is really a great community where people talk a lot about these issues around data quality and assurance and various things. There's been a lot of really interesting tools and support that have been created there around supporting surveys and behavioral research more generally. So I'm going to be talking about some examples of looking at data quality, particularly for free-form text responses. So imagine as a very simple example, I might ask people, what's the capital of Texas? I might get 3 responses like this. And the classic thing we would do is do something like majority voting, trying to figure out what we think is maybe the right answer in a question like this, where it's an objective task, we think with a correct answer. So for something like this, you could say 2 out of 3 people say Austin, you might think that's the right answer, say. And if you look at, though, a much wider range of tasks, this is the sort of thing that people in computer science have typically been thinking about in terms of creating labeled data sets for training classifiers or evaluating them. So if we have just a couple of categorical responses, this could be like sentiment analysis or assigning images to categories, multiple choice questions, where we're trying to sort of say best out of A through E for a given question, ordinal rating tasks, etc. And so this is used in sort of crowdsourcing context when we're trying to sort of evaluate, we're trying to put together, annotations from less reliable annotators, but also even say with medical annotations from doctors where there's not really a right answer, but we want to try to reason about the best wisdom of crowd answer across a group of people. So typically, again, my work's been in this space where we have an objective or correct true answer. But sometimes things are much more open-ended. We often refer to these as subjective tasks. So you might ask someone in this case to transcribe an image, and you get lots of different, or not transcribe an image, but sort of caption it, you get lots of different responses. And the thing is, what do you do in this kind of case to reason about, either what's a right answer or more generally, what's sort of a normative answer or what's an outlier answer in this kind of space? So this is the kind of thing where majority voting is classically employed, falls short because the space of possible options is so large that you can't do simple things like exact match. And more generally, if you look across the kinds of things that people are doing in annotation tasks, there's all kinds of stuff like this, that these sort of simple models for putting different responses together don't work. So if you ask people to rank, say, the top 10 US imports, or to make some complicated linguistic structure, or to say mark spans of text doing highlighting tasks. So the work I'll be talking about today, this is what my PhD student, Alex Braylon, has been leading. The URL for his GitHub repo is going to be at the top of the slides for the rest of the talk. It's available with a very permissive license, and hopefully it'll be useful to some of y'all. So order of the talk, I'll talk a little bit about some prior work in this space, what we're doing, some example outputs, and I'll wrap up. So in that human computation and crowdsourcing community I mentioned earlier, there have been hundreds of papers on people trying to have very clever models for reasoning about response quality and combining things together. But typically they're all on these sort of very simple classification tasks, like say there's a set of categories and reasoning about what the right answer should be. When you try to look at these sort of more complex tasks, we're talking about, say, open-ended text responses, just essentially none of these things work. So what people have done instead is, so for a variety of like more complicated annotation tasks, for every different task they think of, they come up with a new complicated model, which is great if you have time to run like a different model for every different thing you want to do and come up with all these things. And so the idea is, just like for these simple tasks where we sort of have one model that works across a lot of things, it would be nice to have one model that just works across a lot of different kinds of responses you might get from people. So that's the goal of the work we've been trying to do, is to have sort of a way to kind of reason about, again, response and respondent equality across lots of different kinds of tasks in a very general way. So talk about our approach. So the key insight we have is that sort of for every task we're looking at, people have what are called sort of evaluation functions or distance functions for reasoning about sort of how close together two responses are. So if you have an objective task where there's a true answer, you might have an evaluation function for saying how closely an answer matches the true answer, or just simply you have, you know, two responses and you can reason something about how close they are. So what we're going to do is we're basically going to take any kinds of responses we get and we'll map them into sort of pairs of distances and do all of our reasoning about that. So basically we get these distance functions off the shelf and then just apply them. And so I'll be focusing on these free text responses or survey questions in this talk today. So here's our example of this cat eating the donut. You're going to get 4 responses like this. And what we'll do is sort of compute pairwise distances between all responses. So in this case, you'll have some distance function. I'll say something more about this. And you might see that all these ones that look kind of similar will have small distances between them, small numbers. Whereas some other one that's very different has some very large number in terms of how far it is away from everything else. And that's sort of the basis of reasoning we'll be applying. So to give a couple dumb examples of distance measures. So a classic thing is called Levenstein distance, where you sort of look for 2 different textual strings, something about how many edit operations you would have to perform to translate one into another. And this, for example, is done at the character level. What we're sort of doing at more of the fancier natural language processing work these days is there's all this stuff on transformer models. You might have heard people talk about Muppet models because everything is named now like Bert or Elmo or Roberta or things like this. But basically in these spaces, what you do is you take text and you sort of map it into this high dimensional space where you basically start to see a lot of interesting relationships emerge. So as this sort of, you know, toy example shows, you'll see on a lot of NLP slides, you know, you can see that in this particular space, you not only see that maybe queen and king and woman and man have some relationship, but also you could say map between queen and woman and king and man or something like this. So the idea is that you could ideally go into some kind of semantic space where you can look at distances between items. So from the framework I'm talking about today, sort of, we don't care about what the distance function is. You can plug anyone in and, you know, that will sort of change the results. And the intuition is the better distance function you use, maybe the more semantic one, the better results you'll get at the end. So general properties of a distance function, this is a little bit of math for a second, is, you know, you typically want to talk about relations are non-negative, so distance should be greater than 0, should be symmetric, so distance is the same no matter which way you measure it between 2 things. Some of these measures we work with actually are asymmetric, but you can symmetrize them without much work. And this notion of the triangle of inequality. And again, not too interesting for today's talk, but to say, you know, we can take sort of mild violations of these things and still stuff works nicely. And so just showing on this slide very quickly for, you know, text, there's different other distance measures. Again, I'm not going to talk about today, or all these for different tasks have sort of different distance measures you can apply. So what we're going to do is calculate these kind of distances like I just talked about. And the idea is you can do that across all of these different kinds of task types. And at the end of the day, you just end up with a distance matrix here. And so that distance matrix on the right-hand side is the thing that is the core of what we'll be reasoning about in our actual model. So now that we have these distance matrices, what do we do? And so I'm going to talk about some set of examples here where the current item, so you imagine this is a current question in which, a survey question in which we have some free text responses. So the current item is shown here in blue. And you might imagine that there's some particular annotator here shown in green, and we can see a history of other questions he's answered, maybe earlier on the survey or on past surveys. So you can see the same green guy showing up in past things he's done in the past. So I'll talk about 3 methods here, which will make more sense kind of as I go through them. So this first method is a generalization of majority voting. So this is sort of the simplest and easiest to apply, and probably good enough in many circumstances. So what we do is for all the responses we have on a particular question, we compute, again, we have all these pairwise distances between them, and we just say for any given response, what is its average distance to all other responses for the same question? And the idea is the thing that is most similar to all the other responses is sort of most normative, or whatever is sort of least similar to all of the responses is sort of the most of an outlier for that particular question. So this is a local approach because it ignores anything about the history or the particular people answering the question. It just sort of says for the current item, let's see how each of the responses relate to one another. So there's total independence between items. You don't have to do any kind of training or modeling across items or history. But there's also, no notion here, again, about maybe if some participants are more insightful or less reliable or something than others. So the other extreme we have, this is the global approach, which we call best available user. And so in this case, can you imagine for a given response, we can see, for a given question, we look at the responses and we see how close you are to sort of everyone else on that question. Over an entire data set, either that's a single survey of many questions or many different surveys, whatever, you can kind of build in general to see a pattern, a profile for each person about how close they tend to be to other people. So do they tend to be more normative? Do they tend to be more of an outlier? And then what you could do is on any given single question when somebody answers, you could just look over the set of people who answered it and say which person tends to be most normative on average, or which person tends to be the most outlier on average. And then reason something about, again, how the quality of their responses or the normative nature of their responses, sort of just based on their history. So basically really ignoring everything they did on the current question they're answering and just seeing kind of what their historical tendency has been. So this is a nice global approach because you can see this person in like the past history items tends to be most central, but it might be on the particular item here shown in blue that this person is maybe far away from everyone else because we ignore that. So ideally, what we would like to do is sort of get the best of both worlds here. So we'd like to have this kind of history-based assessment of what the person's done historically, as well as looking on the current item, how central they are. And I want to build on this sort of very rich history of modeling we have on this in a crowdsourcing human computation community on these Bayesian models for reasoning about annotations, but generalize them to support these distance matrices we're talking about. So I have a bit of math for a couple of slides, but I'm going to try to sort of give nice pictures to go over everything as I do. So the key technique we're building on is called multidimensional scaling, which has been around since the 70s, so forever. But what we're doing is, whereas multidimensional scaling is over sort of a single distance matrix, we have a set of distance matrices. There's one distance matrix basically for every response, every question being asked. And so our approach we call multidimensional annotation scaling, or MAS. And so this is going to be, again, based on multidimensional scaling, but we're going to turn it into a hierarchical Bayesian model where we have some priors for reasoning about sort of past behaviors. And in general, we want to sort of have some shared parameters across responses. So the first part of when you have a Bayesian model, there's the likelihood term. This is the part this is sort of vanilla multidimensional scaling from history. So for this current observation, we have this current response where we have these captions for the image. We want to take these observed distances we see about how far the responses are and project them into some coordinate space, some embedding, such that the responses that are observed to be close together are very close together in this sort of embedded space. So you sort of imagine we warp the space like this, such that things that are observed to be close together are close together in sort of this embedding space, and this one that's far apart kind of becomes far away. The second part where this starts to become new is where we introduce this prior. So we sort of assume at the origin of this coordinate space is the sort of most central ideal response you want to have. And then the model basically penalizes the number of responses that are sort of far away from this. So if you have a bunch of responses that are all really similar to one another, the model is going to want to pull them closer to this origin because it'll pay less penalty versus this one that's farther away. So again, I'm going to skip a lot of the mathy stuff. And so these terms that are sort of all clustered together get sucked in to be closer to the origin. But we don't have anything yet really saying something about this sort of annotator reliability or sort of trust. And so that's the last thing, this sort of gamma term. So again, I'm not going to assume necessarily correctness. This might just be which annotators tend to be most normative, most like everyone else, which respondents are most like everyone else historically versus ones that tend to be outliers. So the smaller this gamma score is the one people who tend to be sort of most normative, most like everyone else. And so again, what we're going to do here is say that smaller gamma scores should be pushed closer to the origin, whereas farther ones should be pushed farther away. So we sort of take advantage of the sort of reliability parameter for the annotator or respondent. And so that gets sucked in a little bit closer. So now normally when I give a talk, I normally have lots of nice experiments and data and results. And this is like the space I normally work in where I have these objective annotation tasks. So in this talk, what I'm doing is taking the same stuff that we have done in this space and trying to show for these kind of subjective survey responses how it might be used as hopefully maybe a starting point for a conversation with folks after this about ways we might explore some more of this together. So here I've got, I think, 4 or 5 of these responses, but I'm just going to show you some actual quick data about this. So here's, I guess, 7 or 9 responses where somebody is, people are providing these different free text responses. And we have 2 columns. So the right column, which is the one that's used to sort the responses from most normative to least normative. This is our fanciest model that's looking at both the history, the global, as well as sort of the local, what's happening on. And then I also show in the center column, the SAD model. This is the one that's only looking at what's happened on the local response. So you can sort of see they were going to order things in slightly different ways. But the rough thing you can see here, again, giving a flavor of this, is sort of the ones that are most like each other, that are sort of most normative, are going to float near the top of our ranking here, whereas the one here that's kind of the least like these others is going to float down towards the bottom. So the top here, we see he always speaks ill about his father. He always speaks ill of his father. He always talks about his father. Whereas there's one down at the bottom about he always talks about his dad behind his back. So the numbers, I would say, aren't too meaningful. Like, I don't think there's an interpretation you want to assign to the numbers shown here, but I think they sort of give you roughly a notion about how far or close things are. So just a little more signal than just looking at the ranking alone. So here's one more example here. So please be sure to take a note of what she says. Please take a note of what she says. Be sure to take a warning notice of what she says. These start to be a little bit farther away until you finally have at the bottom here something about, please, make sure to insert a disclaimer about what she says, or something like this, memo. As long as you stay quiet, you can stay here. You can stay here as long as you keep quiet. You may stay here if you keep quiet. Versus the bottom, you may be here if you keep quiet. Go ahead. Please go ahead if I'm late. Please go ahead if I'm late, if I'm delayed. And then at the bottom, if I should be late, go without me. And I think one last one. Actually, they are not married. To tell the truth, they are not a couple. To tell the truth, they are not a married couple. And then down at the bottom, 2 people are not couples in truth. So that's just some sort of examples output. So with that, let me just sort of wrap up. So we have this probabilistic model. Again, the problems that we've been hitting it with this hammer are these objective annotation tasks, mostly where we think there's a correct answer. But I think there's utility here in looking at these space for sort of more of these subjective freeform questions. So the work I just showed was with a very simple distance function, really where we were just looking at simplistic distance measures. So I think there's a lot of more flexible, interesting things with more powerful distance measures we could use, but haven't yet. We have a couple models. We have this open source thing with a nice permissive license. So again, where we're going is to more subjective tasks. I think it'd be interesting to do, again, some actual evaluation on survey data with behavioral scientists to see if this stuff is useful at all for folks in practice, and to kind of look at some of the different distance functions or model settings we could play with to maybe make this more useful. And we're also doing some work that I'm not talking about today about looking at detection of consistent biases in participant responses kind of versus what's most group normative. So with that, here are the two key papers for my students' work so far. The one at the top is the main one I talked about. We really appreciate the crowd who provide a lot of the work and annotations that make our research possible. I've got some notes here for the sponsors. Thanks for having me here today.